margin with the properties that f double prime is less than zero for all x less than 0, and f double prime is greater than 0 for all x bigger than 0. So as you guys remember, the double derivative, okay, when it's telling you that we're going from negative to positive, this is talking about, so f double derivative is talking about concavity which means we're talking about inflection point, okay? So it's concaving differently and then at 0. So we are going from, on the left side of 0, it's concaving downward, and on the right side, it's concaving upward. So it looks like we have an inflection point at x equals to 0. So that's it. That's just that easy for A. Now on B, I understand that if you guys printed your notes earlier, this is not going to be here. Neither these graphs here. So can you guys take a minute and sketch it in or write it in before we start? If we have to, can you just pause this video, copy all of those down, okay? B, sketch a continuous, okay, mind you, continuous curve of f equals f of x with the following properties. Label coordinates where possible. So I'm gonna go, looks like our x values here is less than 0 all the way to beyond 5. So I'm gonna go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the y value goes up to higher than 8. So I'll go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So here's the description. On the left side, okay, of 0, it says falling and concaving up. Falling is describing the slope. Okay, falling is another way of saying decreasing. Okay, so on the left side of 0, it says falling and concaving up. And the next time it says, okay, well, at x equals to 0, I'm going to go up 2. I'm going to do all the ones I know how to do. And then 3, 5, ooh, I have an inflection point, okay? So 3, 5, make sure 3 up, 2, 3, 4, 5, right there. Make sure I keep that in mind. 5, 8 horizontal tangents. So it looks like, students, we have 2 horizontal tangents. So make sure I keep that in mind, okay? So 5, 2, 4, 5, and then this was by 10. So there you go. So if I have a horizontal tangent and I have an inflection point at 3, 5. So falling, concaving up, all the stuff on the left side. So concave up must go like that, and that's the slope is falling. Perfect. And then next at 0, 2, I have a horizontal tangent. So the guys, I have to round that out. And from 0 to 3 here, the slope is increasing and concaving up. So increasing and concaving up. So it goes like that. Okay, so I'm gonna erase this slightly. Concaving and, okay, perfect. At 3, 5, I know I have an inflection point. So that means on the other side, it should be concaving down, right? So that's exactly what it should say. Rising and concaving down. Just like that. And then I have a horizontal tangent, meaning that I should be roundabout, and that's exactly what I expected. Falling, which is decreasing, and concaving downward. Voila! And that's how you sketch, baby. Okay guys, this section was quite long. Okay, so let's try to put a summary together. Okay, this is what this whole section is really about. Number 1, differentiable function, let's call it y equals f of x, means f of x is smooth continuous and may or may not have increasing or decreasing interval. Okay, so how about first derivative test? Y prime, that's positive, meaning increase from left to right and maybe wavy. Okay, so if your first test is derivative, it may have an increase and it may be wavy. Okay, this is an f of x function. Now y prime, that's negative, it means it's a decreasing function, so decrease from left to right and again, and maybe wavy. So your could be like this. All right, so again, this is f of x. We're using first derivative to test about increase, decrease. Now second derivative, y double prime, that is bigger than 0, we are talking about concavity. Okay, so if it's positive, concave up, should have no waves, and f of x may rise or fall. Okay, what does that mean? So here's f of x function, concave up. That means that's increasing, as you can see. And then it also have a concave up, but could be a decreasing function. Okay. Now double derivative, if it's less than 0, we know by now that it I can't spell concave. Concave. Look at that. Concave down. Okay, no waves. And f of x may rise or fall. Okay, similarly, we know that it concaves down, so this is an increasing function. And then this is going to be a decreasing function, even though it's concaving down. So concavity does not necessarily equate to increase or decrease, right? Now 6 is your inflection point, which also deals with double derivative. Okay, inflection point is when double derivative sign changes, and remember, tangent exists, right? Because first derivative must exist. So something like this. Oh, there you go. That's your IP. We could also go the other way, right? But the most important part here, guys, that the tangent f prime of x exists. Okay, 7. Y prime changes sign. That means f of x has a local min or a local max. Okay, so 2 cases. If it changes here, this is increasing to decreasing, so there's an L max. If it changes from decrease to an increase, then you are going to have an L min. Okay, so this is L max and this is L min. 8. If y prime equals to 0 and f double prime is negative at x equals to c, then f of x is a local max at C. Okay. So L prime equals to 0, meaning that you have a horizontal tangent, right? And it's a horizontal tangent. And if this is talking about double derivative, that's talking about concavity downward. So concave down. So if it's talking about concave down, then obviously this will be a local max. Last one. If you have y prime equals to 0 and double derivative is concaving up, which is positive, at x equals to c, then f of x is a local min at c. Similarly, right, if you got y prime being 0, that means you have a horizontal tangent, and double derivative is positive, that means you're concaving up. If you're concaving up and you have a horizontal tangent, then this would be an L min, and this I'm going to write L max on the top. And that's everything.